So this is example number 1 for Kelvin circulation theorem. In this particular example, what we have a Stirling flow that actually it looks something like this, and is given by two streamline functions. So this is streamline function number 1. This is streamline function number 2. Okay, and one thing that I do want to point out is that as these particular problems, in these particular problems, what you have is uh, that is function of phi, x, and r. So what I am saying is your cylindrical coordinate system is no longer r, theta, and z. Okay, your cylindrical coordinate system is going to be r, phi, and x. So all you have to do is replace theta for phi and z for x, and it's still valid. And this is how this problem is formulated. And the function that you have here, these are the values of the function at the beginning of your flow, and this is how your flow is varying as it's moving along the x-axis. Okay, and then in this problem as well, you can see r has the following function, and this is valid for a less than 0. Okay, this is how this actually varies. This is how these equations are related to each other. Okay, so let's move on. The question that you've been asked for is, let's find each one of the velocity components. Okay, to find the velocity components, we have to go back to the first thing is the velocity component, and then you ask for to determine if flow is compressible or it's not. So if you remember, going back to the beginning of the discussion, your velocity component is nothing else than the cross product of streamline 1 and streamline 2, where your gradient is actually in the cylindrical coordinate system is given by following. I'm going to write the gradient as we had it in our class notes, and then I will fix it for this particular problem. Just give me 1 second. It's partial of z and ez. Now, in our problem, this is what we had in class, okay? In our problem, now what you have to keep in mind is instead of theta, right? Instead of theta, I have phi. Instead of z, I have x. Okay, so in that sense, my new gradient, I can write my new gradient in the following form: is partial of partial of er respect to r plus 1 over r partial of phi respect to e phi plus partial of z respect to ez. Okay, so we have your streamline function, and your streamline function says that phi1 is equal to, write down the function, is equal to 1/2 u infinite in r squared 1 minus 2ax, okay? And phi2 is equal to phi minus bx. Okay, these are the two streamline functions. So we are going to go ahead and apply the gradient to each one of them individually, and let's see what we get. So I'm going to take this to the next page. Okay, this is your first streamline function, and then your gradient of phi1 is going to equal to the partial of phi. So it's equal to partial of phi1 respect to r, er, plus 1 over r, partial of phi1 respect to phi, e phi, plus partial of x respect to x. Okay. Now, if you do the derivative respect to r, you can show that you get u infinite r, 1 minus 2ax er, plus 0, there's no phi there, plus, and this gives you minus actually, u infinite r square a I. Okay, that's the x direction, so it's in the I direction. Okay, remember ex is actually equal to j, I. So this is the streamline function number 1. Now if I do the streamline function number 2, we apply the same thing for next streamline. So let's find the gradient of this. The gradient of psi 2 will be partial of psi 2 respect to r, er, plus 1 over r, partial of psi 2 respect to phi, e phi, plus partial of psi 2 respect to, x times ex. So when I evaluate all this, the first one gives me 0. This is not a function of x. This one gives me only 1. So it gives me 1 over r e phi. This one is minus b. So it's really minus b. Ex is actually I. Okay, so now I have my streamline functions, and I went into the cross product. So v is going to equal to the gradient of 1 times the cross product of gradient of 2, and that gives you er, e phi, ex, okay? And remember, ex is equal to I. So this is partial of phi1, psi 1 dr. I got a 0 here. I have a term here, okay? I had a 0 there, and I had a term here, partial of psi 2 respect to phi, partial of psi 2 respect to x, okay? So now you can do the whole expression here, and you can replace all those values and do a little bit of mathematics, and you can show that your v is actually equal to minus 1 over r minus u infinite r square a times 1 er minus u infinite r 1 minus 2ax times 1 minus b e phi plus 1 over r u infinite r 1 minus 2ax times 1 ei. Okay, so now I can further simplify all this, collect all the terms, and then your final velocity is actually equal to following. It's equal to u infinite r a e r plus u infinite r b 1 minus 2 times ax e phi plus u infinite 1 minus 2a x I. So by looking at the problem, this is your UR, this is U phi, and this is UX. So those are the components that we were looking for in the problem. Now, the second question that the problem is asking, if you go back to the problem, is show that the flow is incompressible. So to show that if the flow is incompressible, all we need to do is take, if you remember, um, sorry, the gradient, the divergence uh, of v, or the velocity, um, gives you, it will be, this is 0 if it's incompressible, and this is not 0 when it is compressible. Okay, so let's go and find the gradient and see what happens. So if I take this dot this, okay, then you basically find the following. You find that ER dot partial of V respect to R plus E phi plus 1 over R times 1 over R partial of V respect to phi plus I partial of V respect to X. Okay? This is dot. This is a dot. It's a dot product. So I'm going to save some time here. I'm just going to give you the final answer on this. So I'm going to show you how all this expression actually looks like. So to save some time, this is your final answer here. You can see that this term is 0, this is 0, this is 0, this term is 0, this goes to 0, but this is not a function of phi. And so you can show that all these terms go to 0 and the other ones have an answer, right? So all these are 0, and you know that this is actually equal to E phi. This has come from our standard derivation in class. So at the end of the day, what you're really, from all this that you have here, the only thing that you're going to end up, and I think we showed this in class, you basically end up with UR times R plus 1 over UR plus U of X over partial of X. That's the only thing that's going to end up in this problem for this particular problem. And this gives you U infinite times A plus U infinite times A. And this will give you minus 2 times UA. This gives you 2 times A infinite A minus 2 infinite A. That gives you 0. So therefore, this gradient is equal to 0. That means that the flow is incompressible. Okay? So that's the proof. So the next question is that we wanted to show that the Kelvin's law is obeyed for any circulation for x bigger than 0 and x equal to 0. And just a reminder, the Kelvin's law says the following. Kelvin law states the following, and I'm going to rearrange this in terms of our variables. This is phi, not theta. This is r, and your x is what goes inboard, outboard. And then you have an angle here. You have a unit vector in terms of the angle phi. Okay, and this is your variation here that goes here, ds. Okay, this is your vector ds. So your Kelvin's law states that when you have this, right, this is your vector b dot ds. Okay, so based on what we learned in class, it says that this is going to equal to 0. Okay, so that's what we want to try to prove here And if it's 0, then Kelvin's law is obeyed. If not, it's not. Okay, so let's go and work this out. So first, we only have your V, your S. Let's go to the next page. So ds is equal to R d phi d phi. Okay, this is your ds. That comes from this angle, right? From the arc length. Okay, the arc length is given by that. I'm sorry, this is d phi. This is a small variation of phi, d. And then once you do that, and you also have your velocity vector in general sense is UR, ER plus U phi, E phi plus UX, I. So that means that V dot ds, right? Take the dot product. The only thing that's remaining is this term right here. Okay, so that would give you U phi R, U phi R d phi. Okay, and then if you go back in our derivation, where we found that your the U phi was equal to U infinite RB 1 minus 2 times AX. Okay, that's what we found up in our previous part A of the problem. So now we're going to just do the integral, the closed integral of B ds is going to equal to the enclosed integral. And remember, it's a circle, right? So the problem is a circle, so we're going to go all the way around the loop. And we go around the loop, that's from the integral will actually go from 0 to 2 pi u infinite r squared b 1 minus 2 times ax d of phi. Okay, and if you do this integration, you find this is equal to 2 pi u infinite r squared b 1 minus 2ax. So this is gamma. So the problem is saying that your gamma, okay, is equal to 2 pi u infinite r squared b 1 minus 2ax. This is for x bigger than 0. When x is equal to 0, okay, we call this gamma sub 0. It gives you, this is 0, so it gives you 2 pi u infinite r sub 0 squared b. Remember that your r was actually equal to r sub 0 square root of 1 minus 2 times ax as well. Okay, so then r sub 0, that's what r sub 0 is. That's the value when x is equal to 0. Okay, this is the value that you get when x is equal to 0. Okay, now given that, let's go ahead and continue our derivation and see what we get. Um, so now we need to take the derivative respect to time, and we showed in class that this is nothing enclosed integral of dv dt dot ds plus the enclosed integral of v d dt times ds. Okay, now this term is equal to 0 because velocity doesn't change with time. This is 0 because velocity does not depend on time. Okay, it's independent of time. So therefore, the only thing that's going to be left in my problem is this term. This term states that d ds or ds, you can see that this is nothing else than your the differential of the velocity. So that means that my Kelvin's theorem using this theorem, this is actually equal to v dot dv. Okay, so let's go and work this out a little bit. So we know that this is the same as the integral of d v squared over 2. We showed that in class, and we showed that was equal to 0. So you know that this side, your right hand side is equal to 0. Let's work with the left hand side. Okay, so using our differential, you can see this is the same as substantial derivative of any quantity. This is the same as this partial time plus the velocity dot the gradient times the gamma, and this is equal to 0 because it's not the function of time. Now, working with the next term, what you have in the problem is, so what you have here is we found that gamma was equal to this, and we know that the gradient is equal to this, so we apply the gradient to this. You can see that this is x. So you can see that this is not a function of phi, so there's not going to be a phi component here. It's only going to be a function of r because I have r. It's going to be a component of x because I have x. So if I take the gradient of gamma, the circulation, you find that's equal to 4 pi u infinite rb 1 minus 2ax er minus 4 pi u infinite r squared ba ex. Okay, so now I take the dot with the velocity, and I will get the following. Okay, so I brought all the components here to have them all together, and the gamma is going to equal to your velocity dot gamma, and that's going to all equal to the following. So if I took the dot product of this times this and this, remember this is nothing else than I as well, and this times this, I would get the following. I would get 4 pi u infinite squared r squared ab 1 minus 2ax, and this one will give you minus 4 pi u squared r squared ab 1 minus 2ax. And you can see that these are the same. So this is actually completely going to equal to your left hand side is also equal to 0. And that means the Kelvin's law is obeyed. Okay. So this completes this exercise. It was 3-part problem. We started with the velocity, we found the circulation, and then we applied the Kelvin's theorem. And the Kelvin's theorem has to apply in order for the flow to make sense, the circulation to make sense.